good afternoon or good evening, wherever it is, whatever it is, wherever you are. Quick reminder that PLC 8 is going to be up and ready to go for Friday. So do the little quiz format, take that, check that box. Homework 4 is posted. We've pretty much covered almost everything we need in order to do most of those questions and problems. We'll finish a few things off today for thermal expansion, and then we're pretty much good to go. I've got the due date set for Thursday after spring break, so you can expect homework quiz number 3 along with homework 4, because we had the celebration with homework 3. Just a reminder, concept quiz number 2 is posted today, so please be sure to take a look at that and knock out a few answers. It is a concept quiz, so please make sure to give me some conceptual reasoning and things like that. Alrighty?
And lastly, spring break. So that we're going to have lab on Friday this week. We'll have spring break all of next week. We don't do anything Monday after spring break anyways. Tuesday after spring break is a holiday, so it's spring break plus the extra day. So that means I'll see you back for class on Wednesday, which is April Fool's Day. So maybe I won't see you back for class. I don't know. Anyway, I don't really see many of you anyways. All right, so that's what we got on our schedule today. So we won't be back doing this until Wednesday after spring break. I will hope to see you in the lab on Friday, though. So we'll go from there and see how it goes. I want to pick up where we left off here, talking about thermal expansion. So the basic idea here is that when heat goes into an object and its temperature increases, the atoms, molecules, whatever they are vibrating a little bit faster, and they're changing their equilibrium positions, right? So as the temperature gets larger, these things are just kind of growing steadily away from each other, okay? And that contributes to an overall increase in the size of the object, because between atoms, or the intermolecular, whatever you like, if that lattice constant is growing at a certain percentage, right? So they all increase by 10%. Well, then the whole thing increases by 10%, and it depends on things like, well, how much size did the thing have to start with? Because 10% of something small is different from 10% of something large. So the amount that it increases size depends on its original size at some other temperature, presumably a lower one. It depends on the actual change in temperature that you decide to take it through, right? If I dump more heat into it and I increase its temperature larger, well, it should get larger. And then the last one is it's material dependent. So some materials are going to, for a given temperature increase, some materials are going to expand this much, some are going to expand this much, some are going to expand that much, right? So the materials are all different, just in the same way that you put heat into a material and you expect a temperature rise, but different materials will change temperatures at different amounts, right? I put in 10 joules of heat into this thing, and its temperature goes up by a little bit. Put 10 joules of heat into that thing, all of a sudden, right, big temperature. So the idea with the thermal expansion is that that coefficient is also a material dependent situation. So so we have the idea that the amount of change in, and by the way, we're only talking one dimension right now. We're only talking length. We'll talk about how to do other ones in a minute, but the amount of, since I'm talking 1D, I will explicitly put 1D in there. So the amount of 1D expansion, in other words, the change in something's length, delta L, right, should depend on those 3 things I mentioned: the temperature change, the original size of the material at some lower temperature, and then also a coefficient which is material dependent. All right, and so what we do is we just say, okay, well, how about we just multiply all three of these things together, and we'll get ourselves out an expression for this delta L. So what we have here is a delta T. We have a L naught. Presumably L naught is occurring at T naught, right? So we're starting at T naught with a length of L naught, and we're proceeding to some later T with some later L. All right, so this thing would be happening at the temperature T naught, and then a material dependent coefficient, which is just known as alpha and has units of 1 over temperature, which I will in this case be talking about centigrade. So we have to simply multiply these together, and we've got what we need. So we'll do alpha, we'll do L naught, and we'll do delta T. All right, and so all three of those together give us the 1D expansion. Now, I was mentioning that you could think about 2D expansion, you could think about 3D expansion, right? In other words, rather than just thinking about an area, rather than thinking about a length, you could be thinking about an area or a volume, okay? And this is sometimes useful, sometimes not. So every now and again, it's kind of useful to think about these things, and sometimes it isn't, because ultimately, for example, in the example that I'm about to do, I have a like a rod. I'm gonna have a steel rod and a brass ring, and I want to fit the ring over the rod, okay? But if I think about the cross-sectional area of the rod, it would be circular. I'm really gonna, so you'd automatically think, oh, well, area, but the area is going to depend on the diameter, and that's the thing that I'm interested in. So I'm going to be thinking about the diameter's increase rather than the area increase. So that's still a way to think about 1D expansion rather than 2D expansion. And the same thing can happen with things that have volumes associated with them. For example, due to global warming, the depths of the oceans, right? In other words, the level of the oceans will be increasing, and you can think of that as just a depth, right? So how much higher is the ocean going to be because the temperature's higher? So you can calculate that. And it turns out it's going to be about 6 feet higher for, I think, a 1 degree, is it something like a 1 degree temperature rise? Something like that. Which is problematic for many of the lower lying countries, like the island, like Sri Lanka and Indonesia and Manhattan, for example. You know, these places are all places that go right down to the water. So a 6 feet increase in the depth of the oceans means that the water is now 6 feet higher. And that's a problem. Not to mention places like Holland. Anyway, let's take a look at area expansion here. So it would be just a situation in which, for example, I could think of a linear increase that way and a linear increase that way, and I could multiply these two things together. So if I thought of a plate or something like this that has dimensions L and W, and I'm going to think about the expansion of the area, I'm interested in how much more area is there going to be. Well, I could certainly do that by looking at the area being equal to L multiplying W. And if I now heat it, right, so I'll call these naughts, L naught, W naught. So if I now heat it, what happens to these things? Well, the new area, this is at, again, temperature T naught. Now at the new temperature, at T1, which is greater than T naught, we have an area which is going to equal L naught plus a little bit, multiplying the W naught plus a little bit, right? And so in some sense, you can use the idea of 1D expansion twice in order to account for the expansion of this thing in two directions. And the same would be true for volume. Were I to deal with a cube, I could have a third term on the end of that, okay? And so if I just kind of roll through this a little bit further, right, this new area will be the old area plus, for example, these things multiplied, those things multiplied, and those things multiplied, right? But if I think about delta L, and delta L is going to be something like this, and then, of course, delta W is also going to be something like this, we're going to think about, let's see, an L naught times a delta in the W, which means L naught times delta in W, alpha W naught and delta T, plus W naught alpha in L, L naught delta T, plus some more higher order terms. Oops, sorry, getting a little bit off there. But anyways, no problems with this. The idea is that there's going to be a term which encompasses how much the area has changed. And now the point I wanted to make about this is mostly for fun. That sometimes you would say that the coefficient in one direction, the coefficient of expansion in one direction is different from the coefficient of expansion in another direction. That's a pretty interesting situation, but we will say that it's actually isotropic, right? In other words, it expands the same way in L as it does in W. And therefore, when I look at this whole overall term, which apparently I wrote off the board here, sorry about that, I will get it back, so we'll move it back a little bit over here. Once I do this, then you're going to notice that these two terms are basically the same term. There's a delta T on the end of this thing right here. So essentially what it works out to be is L naught W naught, which is the original area, plus 2 times alpha, and then L naught W naught again, times delta T. So, right, it's basically this, so the whole point of this is to say, look, oh, and by the way, for those of you who are sharp-eyed, the sharp-eyed folks are saying, hey, wait a sec, you didn't FOIL that properly. And you know what, you're right, I didn't, because I left off the last term, which would have encompassed a delta L multiplying a delta W, but now you're talking about something that's second order in a very small number, so we're ignoring that, okay? If I look at this, it essentially approximates the original area plus the original area times the change in temperature times the material coefficient, and that happens to just be twice the linear coefficient. All right, so we can actually write out an easy expression for delta in area, which is 2 alphas times the original area times the change in temperature. And so you can do the same thing for volumes. Really kind of nice, right? This is as long as it expands equally at the same rate in both directions, which is a fairly typical situation, right? So for completeness, I could put the volume up here. Delta in volume would be 3 alphas. If I knew the linear expansion coefficient in one of the directions, and it was the same in all three, it'd be 3 of those. You'd multiply by the original volume, you'd multiply by the change in temperature. Quite often, that 3 alpha is known as beta, which is just the coefficient of volume expansion. Sometimes those are known because those are pretty easy to measure, right? So this would be a volume expansion coefficient rather than a linear expansion coefficient. Okay, but nonetheless, this is all just happiness and wonderful fun and games. So what I want to do is go back to 1D and take a look at a situation that I was telling you about. I have a brass ring and I want to slip that over a steel rod. And when I'm starting them off, they've got different sizes. I'm going to heat them both up. I'm going to wait for them to expand, and then I want the ring to be able to go over the steel rod. All right, so we'll do this. We've got a brass ring and a steel rod. Wrong side. Is that the wrong side? That's the wrong side. Darn it. It's this way. There we go. Okay, so here's our brass rod, and I'm sorry, our brass ring, and it has a diameter here of the hole, and that diameter is slightly smaller, okay, than the steel rod. Okay, the steel rod here is slightly larger than this thing here, so we're going to say like this. Okay, so hopefully the way I've drawn it, you can see that the hole here is not quite large enough to fit over the brass ring, the steel rod. So what I'm going to try and do now, this is the kind of T-knot situation. What I want to do is now heat them both up such that the ring expands, the steel rod expands, but they do expand at different rates. I want to heat them up such that the diameters are equal, and that at that point, the ring will slip over and fit snugly on top of the steel rod. All right, so we're going to say that the inner diameter of this ring here, D, I'm going to call that the D of the brass, and the diameter here of the steel, which I'll call D of the steel. These are the starting values. All right, so this is all occurring at our initial temperature. Okay, so now after heating, the ring will fit onto the rod. The question is, what temperature is that going to be? All right, so at what temperature do I have to get these things at what temperature do I have to get these things to in order that happens? All right, so let's take a look. And okay, let's take a quick look. So what I'm shooting for, my goal, is basically to have D of the brass ring, right, plus delta D of the brass ring, right? And when I heated it, it's expanded, right? And oh, by the way, before we go a little further, I'm talking about the hole in the ring here, right? I'm talking about this opening. So maybe you think about, hey, wait a minute, why when you heat the ring up, let me just do a quick couple of drawings down here. Why when you heat the ring up, so the question is, I start with the ring looking like this, and I heat the ring, and what do I get? Do I get something that looks like this? Right, where the thermal expansion has caused the edges of this, if it's like a ring or a washer, right? It's caused the washer to expand such that the hole has kind of been filled in a little bit by the expanding material. Or do I get something that looks like this, where I draw this? Like that, where the hole actually gets larger even though I'm heating it and there's nothing in there. Yeah? So if I get a heated ring, which one's it going to be? Well, given the constraints of this problem, how I've set it up, hopefully you understand it's going to be that one. But an interesting set of arguments could lead you to this one, right? So why is this one not what's happening? And that one is the one that's happening. Well, a couple of different ways to think about why this happens versus this. And one thing to think about is the inner circumference. That's also a linear measurement, right? The inner circumference of the ring inside here, that's a linear measurement, right? That's not area. It's around a circle, right? But it's a linear measurement. That circumference, as I heat the thing, has to increase in size, right? Which means the hole has to increase in size. Another way to think about it, if I consider the piece that I cut out of this ring in order to make the hole here, and then I heated that thing up, wouldn't that get larger? Well, okay, if I put that back into the ring and then I heated them both up, wouldn't they both get larger? Right? So ways to think about what's going on. It turns out that's the situation with the heated ring. You get the larger opening rather than the expanded material. Okay, so just thinking about what's going on here. My goal, back to the goal. All right, back to the goal. The brass ring diameter should equal the steel diameter at this new temperature. Okay, so what I'm doing is I'm writing out what is the new diameter at the hotter temperature. Okay. All right. Okay. Now, in terms of knowns, we do know most of the things. Okay, so in other words, we know things like the initial temperature. We're going to consider that a known. We're going to be solving for the final temperature. That's what we're looking for, and hopefully we can understand that the initial diameters we know, the coefficient expansion rates we know, so all of that type of thing. What I want to do here is just see if I can pull out what is the common final temperature from this expression so that we can just solve one thing instead of trying to run through a bunch of numbers here. All right, so these things here are going to be alpha of brass times the initial diameter of brass times the temperature change. And this one here is going to be the alpha for steel, the initial diameter of the steel, and the same temperature rise. Okay, because they started at the same temperature, they're going to end at the same temperature. So those delta T's should be the same. Therefore, if I'm trying to solve for that delta T, what I'm going to get, what do I need to do here? I need to take 1 over to the other side and do things like that. So, all right, let's suppose that in the initial case, we know that the steel rod is larger. So I'm going to take the brass diameter over to that side, and I'm going to take the delta S of the delta diameter in the steel to this side, because that's got to be less. So I'm going to try and end up with 2 positive quantities here, right? Because this thing is bigger than the inner diameter, so ds minus dB should be positive, which means this doesn't need to expand quite as much as this does, so therefore delta dB should be larger than delta ds. All right, so what I have then is it's going to be delta D minus delta D equaling ds minus dB. And for each one of those delta changes in the diameter, I'm going to put in the expression that I have for them here, and I'm going to factor out the delta t. All right, so my delta t, from both of those things, I can just pull out to the front of this expression here, and then I'm going to get the difference in the first 2 things, brass and diameter minus steel and diameter, and that's going to equal steel minus brass, like so. And all I got to do is swing that underneath, and I should be able to be good to go to find what the temperature change is going to be in order to affect the necessary expansions. I've got alpha and B, delta. I've got a, what did I put? I wrote an S here. That should be a B. That should be a B, and that's minus S and S. Like so. Let's see here. Did I get that all right? All my symbols look good? S minus B over alpha B D, B minus alpha S ds looks okay. All right. I think that's what we got for an expression. Let's pop a few numbers in and see. We'll start with the diameters being fairly close, but not quite exact, right? So let's suppose then that we have things like the brass diameter of the hole, right, here being 2.99, let's see, what did I want this to be? 2.992 centimeters. Yep, 2.992 centimeters. And the diameter here being 3 centimeters. All right, so what we have to do is expand this hole by 8/1000ths of a centimeter. That's all we're trying to do. 8/1000ths of a centimeter, that's 8 times 10 to the minus 5th of a centimeter. No, that's 1,000th of a centimeter. 10 to the minus 5th of a meter. So that's in the micron range, right? That's 80 microns. 80 times 10 to the minus 6 meters. So that's not a big amount. That's not a very large amount to be doing this. Let's take a look. What did I have for my initial temperature? We'll start at 25 centigrade, and we can look up what the alpha of brass and the alpha of steel is, and it turns out that we'll start with T naught equaling 25 centigrade, and alpha of brass is 19 times 10 to the minus 6th per centigrade. Let me make sure I'm writing this number down right. Brass is 19 times 10 to the minus 6, and steel is 10 to the, or is 11 times 10 to the minus 6 per centigrade. So you can see these things aren't really expanding a whole bunch, right? This is not a huge phenomenon for small items, right? It's a huge phenomenon for large items, like I was talking about last time, the Golden Gate Bridge. That's a large thing, and it expands by a lot because of its original size. These are small, so they're not gonna, right? The rates are pretty small. All right, so when you plug all this stuff in, if I put in the centimeter difference up here and the alpha times the original diameters here, I find a temperature difference of, let's see here, I think 360 centigrades. Is that, wait a second, is that the actual temperature or is that the temperature change? Well, that's the actual temperature, sorry. So the temperature change is 335. Right, so I'm aiming then for a final temperature of 360. Okay, starting at 25 centigrade, I know the change as I solve for it here is 335, so my final is 360. All right, and that's the temperature at which these two things should fit snugly. If I then cool them down, the brass ring pinches onto the steel rod and it will not be removable. Yeah, so you can heat them back up and then you could probably pry it off. But once you cool this back down, it's going to be basically cinched and it won't come off. Okay, which is the basic idea of the rivet. Okay. Well, back that up. The basic idea of the rivet does not use different materials so that they don't expand at different rates. They have this one, you heat this one way up, you put it on this one, and they have the same rates of expansion. So that when you cool this one off, it cinches here, now you heat it back up to get them off, but they're both expanding and they won't come off. That's a rivet. This is a little different. Okay, so there's a little bit on thermal expansion and what to do with these things. And we talked a little bit about area and we talked a little bit about volume. So I think that looks pretty good for now. Let's do this. I'm gonna wrap up basically what we've talked about in terms of the first law. I want to try and put all of this stuff together. Oh wait, no, I want to do one other thing before we leave thermal expansion. Hold on. There's one big exception. Can't really not talk about the one big exception. You know what the one big exception is, I would imagine. To thermal expansion. Right? Liquid water. What does water do when you cool it to become ice? Right? By the way, and I have not verified this statement, but I believe it to be pretty much true, which is that water is the only naturally occurring substance that does this. And I'm pretty sure that's not 100% true, but I really think that it should be. That it expands. In other words, its solid floats in its liquid. It's one of the only substances naturally occurring for which this is true. Okay, almost every other substance that I can think of, now naturally we can make this happen. That's fine. We can engineer things to do this. But naturally occurring, the idea that the solid of a material floats in the liquid of the material, almost unheard of, right? Almost unheard of. Yet it's so common because of the prevalence of water. So let's examine what's going on here. The curious case of water. So we know that, let's do this. We know that solid water floats in liquid water, which is a very strange set of things to happen. That tells us that the density of the solid is less than the density of the liquid. In other words, for the same mass of stuff, the solid takes up more space than the liquid does. Just really kind of not usual, okay? So density of ice is less than the density of liquid. Okay, so why does that happen? Let's take a look here at what happens. Now, let's see, I think I have, do I have well, I don't know if I have the picture for it here. Well, let's take a look at the density. Um, if I draw a graph of density of water density of water versus temperature, right? So I start with some amount of water at some temperature, say, I don't know, 30 or 25 centigrade, okay? And I'm cooling the liquid down, okay? So we'll start here. It's going to be a bit protracted, but we'll go like this. So 0 centigrade would be right here on the axis. This will be 0 centigrade here. We'll start at something like 30 centigrade, okay? So everything is totally normal for water as you cool it, okay? So we've been talking about what happens when you heat something, right? If I put heat in, the temperature goes up. The opposite by whatever extension, the opposite is also true. In other words, if I get heat out of something, I cool this thing, right? I lower this thing's temperature, it contracts. And liquid water totally does that, all right? Liquid water totally does that. And you could start with it even way up at 90 degrees centigrade, right? And as you cool it, it will shrink, okay? So you find that it shrinks down as you cool it. This is exactly what you would expect to happen. When you cool something, it contracts. And liquid water totally does this. Until, let's see here, what is this, 5, 10, 15, 20, 25, 30, so we'll go 4, 8, 12, 16, 20, 24, 28, 30, well, it's about there. So we're going to go like this. We're going to come down, 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 and eventually right around here, it stops shrinking and starts expanding. And so this has been studied. At what temperature does this happen? The temperature at which this happens is 4 centigrade, where the lowest, this is the lowest density. Wait a sec. I'm doing density. I shouldn't be doing density. Oh, it should be the other way if I'm doing density. Okay, so flip this over. Sorry. I was thinking volume and then I talked density. Okay, hold it. Sorry. It shrinks. So the density should be going the other way. Okay, so fine. That's fine. It should be going the other way. Sorry. I was thinking volume when I'm drawing this. It's shrinking its volume, but density is the other way. Okay, we'll start that over. Density goes like this. Like that. Okay. Man, I guess it's time for spring break. Okay, right there, 4 centigrade. So this is the largest density that it has. In other words, the amount of water has contracted and contracted and contracted and contracted, and it takes up the least amount of space here at the highest density. And then when you cool it further, it expands, 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 expands. All right, so this is the largest density. Like this. And what that means is water of 4 centigrade is dense and will sink in any other temperature liquid water, right? Because if you increase the temperature, right? If I take a packet of 4 centigrade water and I go to a lake that's 20 centigrade and I put it in it's going to drop because a more dense object will sink in less dense surroundings. That's why one of the reasons why we stand on the surface of Earth. We don't just float around because we're more dense than the air. On the other side, if I take my 4 centigrade water and I go to a lake which is at 1 centigrade, and I put that into there, it's still going to drop because the 1 centigrade water is slightly less dense than the 4 centigrade water. Really weird. But ultimately what happens, so when it hits ice, it's become less dense. What happens here is that some of the crystals in some of the molecules in the water start to form pre-crystal ice structures. Okay, so even though it's not at the freezing temperature, you get a little bit of pre-freezing happening. And the pre-freezing, we'll talk more about that a little bit later, but the pre-freezing happens, and what goes on with ice is that it's an open structure. So when it's a liquid, all of the H2O molecules are jiving right real close to each other like this, but once they get to a crystal, they go and they make the big open, like hexagonal. I mean, if you've ever seen a micrograph of a snowflake, right? There's a lot of space in there, right? So the liquid is starting to pre-freeze, and it makes these bigger open structures, which increases the volume and therefore drops the density. And that ultimately, when the whole sample of water freezes, it freezes into these big open structures, which is why the ice floats in the liquid. So this is one, like I said, one outstanding case of the idea of thermal expansion. So between 0 and 4 centigrade, water is the opposite, but it's only in that little temperature range where it's not thermal expansion, it's thermal contraction. Right? So if you heat up this stuff, it actually shrinks. And then once you keep heating it past 4 centigrade, it increases its volume. So we're actually really happy for that as creatures on this earth, because what that means is that when it's a very freezing cold night outside, okay, let's see, when it's a freezing cold night outside, and I have a lake. What am I doing? What the heck kind of diagram is this? I have a lake here, right? And there's this really deep lake. And if it's really, really cold here, temperature is way less than 0 centigrade out here. But what that means is ice will form on the top of the lake, but at the bottom of the lake will be 4 centigrade water because it's dropped all the way to the bottom, right? And then the ice on top actually forms a thermal insulation barrier to heat escaping, right? This would be ice. Right? So the lake freezes top down, and if it's a deep enough lake, the heat that would be leaving from all of this water can't get out because the liquid is as dense as it's going to be down here. And so down here is where all the little, algae and pond scum that we evolved from can live. And so when it's really cold outside, like it's a ice age, there's still a little bit of liquid water around to keep the animals alive. Whatever these are they even animals? I don't know. But anyways, there's some life. Life's going on. There you go. Life happens. So there's that. So we are happy for this because our ancestors came from that pond scum at the bottom of the lake. Oh boy. All right. Sorry. Hope I'm not hearing about that one too much. Okay. Anyways. Good. So there's that. I want to recap a little bit on what we've done with the first law. So let's do that here. We've gone through 4 processes of the, this is a review of first law stuff. Okay, we've gone through 4 processes. Ultimately, the first law is all about energy conservation on the, what I call, microscopic level. So not that you can see the molecules or anything, you can't. So even if you put them under a microscope, you're not going to see them. But I refer to microscopic as being the really small, and that's what molecules really are. Atoms are also consequently quite small. It's about energy conservation at that level, really, really little level, okay? And it's the idea that the internal energies of these materials is affected by heat and work, and typically we say that the internal energy is related to the temperature. Now that's if it's an ideal gas, and I talked about last time the bond energy, right? That could also be, if you're thinking of a liquid, the bond energy would be a delta E internal. That's part of the internal energy. But calculationally, if we're talking about ideal gases, it's temperature change only here because we're only referring to the kinetic energies involved. So we have that. We have PV diagrams in which we talked about 4 different types of processes, right? We talked about these. We talked about those. Let's do this. I don't know, whichever. I mean, I'm putting arrows on them, but it really doesn't matter. They could go either way. We talked about these, and then we also talked about those. Okay, so if I were to call out what we have here, we have isobaric. In other words, constant pressure here. We have isovolumetric. For the constant volume process here, work is not done in this process. This is a situation with fixed boundaries of your system. One of these is isothermal. It's the more shallow one. Isothermal is the one in which the change in temperature is 0, and then the adiabatic is this one here in which there is no heat transfer allowed. That's the adiabatic right there. So those are our 4 processes. Not to say that we're only going to use those 4, but they are the 4 reasonably most common ones that we're going to take a ideal gas, a thermodynamic system from one state to another. Okay, we have examined work. Okay, we've examined how to calculate what the work is on something. Okay. Remember our sign convention, positive if something's coming into the system, negative if it's leaving the system. We've talked about bar charts and cylinder diagrams. So thinking about these processes and thinking about a piston cylinder. Okay, I can do different things with a piston cylinder. So I can do things like put a mass on top. I can insulate it to stop heat from going in and out. I can heat it with a flame. I could lock the piston in place so that it cannot move and I have a fixed boundary, a fixed volume situation, right? I can do a lot of different things, but all of what the situations we've talked about have only been in the constant amount of material range, right? So in other words, I've kept the same amount of gas in the cylinder here for pretty much all of these processes. I don't think we've talked about material coming in or out. So for right now, our amount of material is constant, and we've looked at what happens to the energies across the boundary. How do I stop energy coming across the boundary? When energy does come across the boundary, what effects does it have on the energies of the particles inside here, the gas, et cetera, et cetera. So thinking about how to draw the cylinder diagrams as well as the bar charts, where I could say, well, look, I've got some internal energy here in the initial state. I'm going to change that. I don't know, some work is going to get done. I'm going to put in a small amount of heat. I don't know. I'm just making this up. But just thinking about what the energy bar charts look like and how to relate all 3 of these diagrams. Okay. So this is not representative of anything particular. I'm just sketching something out here. Alrighty, so we've done those 3 diagrams to help us with keeping track of what the energies are doing, how we make those energies change. We've also talked about temperature scales. How do we measure temperature? We've talked about temperature scales, and specifically the centigrade and Kelvin scale, which are the ones we're mostly going to be using. We've talked about the ideal gas equation of state. I have not really gone into what little n is, but we will be doing that in a little while. Well, possibly a little bit later in this session, or possibly next time I see you, which is going to be like in 400 weeks. Pressure, volume, and temperature for the ideal gas equation of state. We have talked about thermal expansion. Let's see, was there anything else that I wanted to go over here? What we had, temperature scales, thermal expansion. Oh, and we did, of course, sensible and latent heats as well. So sensible and latent heat, and then we just finished off the thermal expansion. So these are all the things we've kind of dealt with here in the our first section in the thermodynamics unit. I mean, I didn't write the laws on there. I was hoping the laws were their own thing. This is just an examination of the first law by itself, and some extras to go along with it. All right, so hopefully that is all there. Okay, so that I think is approximately what we've talked about in this first section on thermo, and I want to spend a little bit of time talking more thoroughly about the ideal gas and what that model is. So that will take up the rest of today. Then when we come back, I'll probably finish a little bit of that off, and we'll start talking about the second law. So I think that's enough for you to be getting off doing the homework. You can get started off doing that. And like I said, the homework is due the Thursday after spring break. So there's a couple of days in there that are built in, but do remember a homework quiz is coming on the same day as the homework is due. So be sure of that. All right. Any questions? Nope. Okay. So here, I want to examine the ideal gas just a little bit more specifically. All right. So this I do what? Climb on the soapbox here? What do I want to say? This is not technically part of classical thermodynamics, and I believe I mentioned this before. Classical thermodynamics does not take any part in dissection of what the ideal gas is made out of or what substances are made out of, right? So this is a bit of a diversion. We all know, and I think we've all been taught this, gosh, really early on, you know, even I remember my kids were in preschool, you know, the preschool teachers were teaching them about the planets and the matter is made of atoms and things like this. They come home, oh, well, did you know that things are made? Oh yeah, how about that? Okay, great. So these little science factoids do kind of make their way into the public consciousness and get distributed somehow so that the grand general, most of the people know about stuff like this. So it's really kind of not useful to avoid it. So let's go ahead and talk about it. Let's look at the, let's start, let's begin dissecting. Let's start dissecting. Let's begin dissection of the ideal gas model. One thing that you will possibly notice, if you have already studied something of this nature before, is that I am omitting the phrase ideal gas law. And I think you can probably see why I'm doing that. In case you missed the first videos on the thermodynamic subject, I went over the 4 thermodynamic laws, and I don't remember ideal gas being one of those. So this is not really a law. It's a model that works well to describe some things, right? And so it's very much on the same level as something like, if you remember from a 4A situation, the spring force is often described by something called Hooke's law. But it's not a law. Newton's laws are laws. Hooke's law is really just something that sometimes applies to some things. Well, it's the same thing with this. Hooke's rule, or the model of spring forces, is quite useful, but it's not generally true, right? And this is quite useful, but not generally true. We will use this to help guide a lot of our thinking, but it's not generally true, okay? So let's look at what's going on. I've mentioned before, my mental model of this is something like independent billiard balls on the table, right? On the pool table. Bum, 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 bum. They don't know anything about any of the other ones until direct contact happens, okay? So in that sense, if I were to think about what does the potential energy graph look like for these things, the energies between these is zero, right? If I think about what the potential energy between, and this R here will be between molecules, right? Between air molecules, say, right? There's a nitrogen molecule here and a nitrogen molecule here. I just grabbed them. And what attraction do they feel? Nothing, right? At least according to us, in order to simplify things. They probably do feel something in reality, but for us, zero, right? 0, 0, 0, 0, 0, 0, 0, 0, until they get so close that they're touching, and that happens. And then it goes all the way up to infinity, potential energy on that axis and R on that axis. So it goes all the way up to infinity because they bounce off each other and they hit and they don't deform. There's nothing. So it's a model, right? The ideal gas, it's a model. There's nothing in nature behaves this way. Well, nothing behaves this way. At least nothing we're going to talk about. So that's nothing. Okay. Let's start trying to understand why things like pressure happen, right? And let's talk about why we talk about the temperature as being related to the kinetic energy, okay? So we'll start off with a little bit of this, and like I said, we'll probably have to come back to this, but let's examine what happens when a gas molecule, right, an air molecule or something like that, bounces off a wall. All right, let's suppose we've got containers of our walls of our container here, and the air is hitting them. Okay, so let's examine the let's have a gas molecule bouncing off a wall here. Okay, just as like I have drawn here, all of these little molecules or these little particles of gas, they're hitting things, right? They're hitting the piston, they're hitting the sides of the container, Okay, let's examine what happens when that's going on. So here's a wall. Let's just assume that the left side is rigid, right? This is a rigidly held thing, and here comes a molecule. It's going to do something like this, right? Suppose it's down here. Here's our molecule. It's going to go, it's going to bash into the wall here. It's going to hit and come off like that, like so. Okay. So if I were to draw the velocities for this thing here, right? The velocity of the thing would be a little bit this way and a little bit this way, right? That would be, let's suppose this is V. I mean, if you just want to call X and Y, let's call standard XY, right? Let's just throw an X set of coordinates on here. So this is Vx initial, and this is Vy initial, okay? Here, after the final, after the hit, and we're in the final state over here, and you can imagine, I mean, I've drawn this with a lot of space, but you can imagine this is fairly close to the collision. It like hits, and we're looking at the velocities. I'm gonna go like this. I've got a Vx final here. I have a Vy final here, like so. Okay. So that the molecule, or whatever, this atom molecule, I'm just going to say molecule, hits this thing and bounces off. So let's assume that we have a collision that we can analyze with 4A techniques, with just standard conservation of momentum and stuff like that. Well, not conservation, but I guess impulse and momentum, maybe. Let's suppose we can think about that. If I examine the momentum of the molecule, right, initially it has some momentum in the negative X direction, and it has some in the positive Y. The positive Y component seems like it would probably be preserved. The X component has definitely changed. So P in the X final minus Px initial is delta P in the X. And if we think about that in the Y, Py final minus Py initial is delta P in the Y direction. But I'm gonna assume, it looks to me like that's gonna be 0 in this case. It looks like the particle came, hit, and bounced off and went that way. So the initial Y momentum and the final Y momentum look to me like they're equal. Right? Therefore, let's calculate how much momentum change happened in the X direction. Well, I had whatever the mass of this thing is times Vx in the initial, and that's negative according to my coordinates, and Vx final is positive, so I'm going to get that m times Vx final plus Vx initial. Right? In the delta, I have a negative in this Vx initial. So it's Vx final minus negative Vx initial. This is going to be a fairly substantial momentum change then, which you know it should be, because the particle was going that way, hit, turned around, came back this way. And momentum's a vector quantity, so we have to be able to say that the change was large due to that. So the question is, what caused that change in momentum? And naturally, Newton raises the hand and goes, I know, I bet you it was a force. Okay, so in the case of impulse and momentum, or if you like, Newton's second law written in the original way, if you like, Newton's second law was that the sum of external forces equals the time rate of change of the momentum of the center mass, and this is a particle, so the particle is the center of mass. Well, we have a change in momentum here, right? We basically have a change in momentum. That's what this is. Let's assume that it's elastic so that the V is preserved here, and I can just refer to this as Vx, right? So we'll evaluate this at Vx final equaling Vx initial. And therefore that the total change in momentum can just be written as two of these, right? Instead of one plus the others, just two of them. Now, if I think of that as delta P in the x, then I can say that the force exerted in the x direction is something alike delta P in the x per time, and that would mean it's 2m times Vx divided by some time interval. The time interval during which the collision happened, right? Right when this thing was in contact with the wall, that's the time of collision, okay? So we might be interested in finding out a little bit more about what that time looks like, okay? And that way we're going to come to an expression for what force is getting exerted by the wall on the particle, and therefore by Newton's third law, what force is the particle exerting on the wall? And that's, well, I just erased my piston cylinder here, but that's important for a piston, right? Because the piston has weight and ultimately is being held up by the pressure of the molecules hitting it, right? And if that happens repeatedly, then they can support the weight of the piston. Okay. So let's take a quick look here at the number of collisions that happen. Now, this is going to be a little bit tricky, okay? Because ultimately what I've done here is I found that this is the force of one molecule hitting the wall. But, like I'm talking about, there are hordes of molecules that are hitting the wall or hitting the piston or whatever you like, okay? And they are right there, they're leaving like, that's a pretty big hit. Well, I mean, for a molecule, right? If you were a molecule, this is pretty like bam. So let's think about how many molecules are hitting the wall. So if this is just the force of one molecule on the wall, or vice versa, really, if it's the force of force of the wall on one molecule. So what would it be on the ones that are hitting it all, right? There's more than just one in here. So what about all the other ones? All the other ones here that have some momentum in that direction and would have hit, right? So the total force exerted by all the molecules of gas within the container are going to be due to those which are traveling that way and would have hit in a certain amount of time. Okay, so let's suppose I call that something like there's a number, right? There's a number of these things. I won't draw them all out right here, but you can imagine there's a number of molecules here, and a lot of them have a velocity or momentum towards the wall. So those will hit in a certain amount of time, and the other ones might not. All right, so let's assume that the total force on the wall due to whichever molecules are close enough, right, is going to be proportional to a capital N, and I'm just going to say that's the number that can make a collision in this amount of time, right? So however many collisions there are, each one of the collisions, say, does something approximately like this, okay? Now, they don't all have the same Vx, but we can use an average, and we'll get into that a little bit later. So the total force on the wall should be proportional to the number of molecules that can make a collision, right? Number of collisions. Multiplied by this force right here, force of one of them. Okay. Let's do this. all right? So now at this point, if I'm going to say that there's, say, within here, I'm going to say there's a certain amount of time during which molecules in here with a leftwards component of momentum are going to hit this, right? So we just got to figure out how many that is, right? So that the total force is equal to the number of collisions multiplying this Fx, force of one molecule in the x direction, all right? So let's see if we can figure out what goes on here. If I say that this thing is equal to number of collisions times 2m Vx divided by time, I can play around with the ordering of these things such that I can swap the time and pull it over here so that I have 2m Vx times the number of collisions per time. And this means I'm really looking at a rate of collisions. Right? This is a how quickly, what's the frequency of these things? What's the frequency of the collisions on the wall here? Okay? So if I consider that there's a certain number of molecules in here per volume, right? I basically have a volume of molecules in here, right? I said I wasn't going to draw them all in here, but you can imagine I've got a bunch of these things in here. If I consider the density of molecules or the density of the gas as being equal to N over V, right? There's a certain number of molecules per volume. And I think of this as a volume, right? Then I can talk about the number which are going to collide, okay? So this number density here, I can think of this volume as being this, right? So I'll just say that there's a certain area. If I were looking at it from this side, let's just assume I'm looking at a particular area, and then that area is multiplied by a distance here, from here to here, right? Which is basically Vx times time. In other words, any molecule that has this Vx in it, if I choose a time large enough, any molecule that has a Vx to the left will hit the wall in this time interval. Okay? So this is going to go into Vx times delta t for the area times the length, and that gives me a volume. Okay? So what happens then is that I can now consider that in thermal equilibrium, what's the chance of a molecule going this way? If I just pick out of all of these molecules in here, if I just pick out all the ones going this way, about what ratio am I going to be picking out? Well, if this is thermal equilibrium, then there's no preference for the molecules to be going one way versus another. That means we'd expect half of them to be going to the right and half of them to be going to the left. Therefore, within here, half of them aren't going to hit the wall because they're going this way. So half of them are because they're going this way, or they have this component of V towards the left. So within this number is really, there's a 1/2 built in. Okay. So when I think of trying to write down how many are making collisions, the number of collisions should equal 1/2, right, of the total density of these things, N over V, the total number density of things multiplied by the volume right here, right? This A times Vx delta T. That should be the number of collisions. So the number of collisions per time simply means when I take this quantity here, all I'm going to do is wipe off this thing here, and that's going to give me an expression for the total force on the wall, 2 mvx, multiplied by 1/2 the density, N over V, multiplied by the area, multiplied by Vx. So that's another Vx, so that means it's Vx here is squared. Okay? Alrighty. Well, look at what we have, right? If I wanted to calculate the pressure, I would do the force per area because that's what the pressure is, which would mean I would take this area, swing it underneath, and then whatever's left over is what the pressure is, right? So here I would end up with, now, it depends on how you like to go about this. You can cancel the 2's, right? You can get rid of these. But if I swing the area underneath here, I'm going to get N over V, which is the density, times mvx squared. And that kind of makes a reasonable amount of sense, yeah? In other words, a gas has a bigger ability to exert pressure if there's a lot more of it, right? In other words, the density of the gas is larger, and also mvx squared here is very similar to a kinetic energy, okay? So if the kinetic energies of the gas is high, right, then they're going to be hitting with a lot more speed and therefore exhibiting a larger momentum change, which is going to cause a bigger force. Bigger force means bigger pressure, and that means you are going to be, as a gas, you're going to be able to sustain bigger weights on top of the piston or something like that. Okay, so from the molecular standpoint, right, if I just consider these molecules as being individual rigid spheres, right, little bouncy spheres, then the pressure exerted by them is related to how many there are, the number density, and basically what kinetic energy they have. So that kind of ties into our intuition of the ideal gas, hopefully, right? Good. We will pick up here. I think that's about time for today. So we'll pick up here on the Wednesday after spring break, and we'll continue talking a little bit more about the kinetics of the ideal gas model. But this is basically the road we're going to travel here. We're going to look at a mechanical analysis of the actual individual particles themselves to try and get some intuition about how the ideal gas model functions and what kind of relationships we can expect to see between things like the pressure and the kinetic energy, or the temperature and the kinetic energy, right? Or the specific heats of these things and the way they have the energies and things like that. All right, so for now, I guess I will bid you happy rest of your day, happy weekend, and I will talk to you later.